Okay, in this video I'll provide a review session for the second half of the course, MBA 6140. This is not a perfect substitute for having actually attended the whole course, but it's a pretty good guide to what we're going to be covering on the exam, at least topically. In particular, the topics I'll cover in this review session are two-part tariffs, bundling, the dominant firm model, homogeneous goods duopoly, expected utility, public goods, and externalities. I'll give examples of problems in each of these areas and solutions and ways of solving the problems. All right, let's start with the two-part tariff problem. In this problem, we'll have two consumers, one of whom has the demand curve P equals 20 minus Q, the other of whom has the demand curve P equals 23 minus Q. Finally, marginal cost of the product is 10. So what does this look like in a picture? Well, if we have quantity on this axis, price on this axis, here's 10, there's constant marginal cost, then the lower demand consumer's demand curve hits this axis at 20, comes down with a slope of minus 1, so it crosses here at 20. The higher demand consumer has a demand curve with an intercept on the price axis at 23. It comes down with a slope of minus 1, hits here at 23. We can also note that the lower demand curve comes through marginal cost at a quantity of 10. How do we know that? We know that because we could have rewritten that demand curve as Q equals 20 minus P. And when it's crossing an MC of 10, if we say 20 minus 10, well, that equals 10, and there's our 10. Similarly, the higher demand consumer's demand curve crosses marginal cost at 13. All right, that's the setup of the problem. Now we want to think about profits in this problem. So, maybe with this picture in mind, let's move over to some clean space and think about how we characterize profits. So profits are going to be the profits that we get from per unit sales. So whatever our price is, price minus that marginal cost, times the number of units that we actually sell. Now what's the number of units we're actually going to sell? Well, remember, one of the consumers had the demand curve Q equals 20 minus P. The other had the demand curve Q equals 23 minus P. That means whatever the price is, if the price is P, then this consumer buys 20 minus P units. So what that means is this is like the profit per unit multiplied by the number of units sold to this person, and that's 20 minus P. Add to that P minus MC times the number of units sold to the other person, 23 minus P. And then finally, in addition to that, we want to add in those triangles, in particular the triangle under the lower demand consumer's demand curve above the price. And so what's that? Well, that's going to be 20 minus P squared divided by 2, but then times 2 because there are two of them. So simplifying this a little bit, keeping in mind this is just a little box, let's use a little bit of what we know and write things down. So we know, for example, that MC is 10 in this problem, so let's just refer to P minus MC as P minus 10. Now let's collect the terms here and here, because they both are multiplying P minus MC. So that means in there we would have 20 plus 23, or 43, minus P, so minus 2P. We add to that then what we have here. The 2's cancel, and we have 20 minus P squared. That's an expression for profit. Now let's go back and do a little bit of economics here. Let's think about what that picture looked like. I'll make a kind of a schematic version of it here. PQ, there's 10, which is MC. Here's that lower demand consumer's demand. Hits this axis at 20. Here's the higher demand consumer's demand. Hits this axis at 23. So let's think about one of the things we considered as we learned this module, or in this module of the course. We thought, well, what if price were equal to marginal cost? Then we know that we get no per unit profits, but we get the area under the lower demand consumer's demand curve above MC as a membership fee, and we get it twice. So let's think about P equals MC and find out what's profit. So P equals MC implies profit equals. Well, MC, of course, is 10 here, so profit then would equal 10 minus 10, which is, of course, 0, times that 43 business minus 2P. That's all 0 because it's got a 0 multiplying it, plus 20 minus 10 quantity squared. And so what's that equal to? Well, that's 0 plus 100, or 100. So all of a sudden we have a benchmark. We're saying if we price at marginal cost, we'll get a profit of 100. This is sort of a strategy for solving problems like this. But if we think back to what we learned in class, we should expect we could do better if we were to charge a price above marginal cost. So let's move on from here and consider some prices above marginal cost. But let's hold this formula in our heads. So here we are. Start again. Let me save you the trouble of holding something in your head and just write that we have P minus 10 times 43 minus 2P plus 20 minus P quantity squared. So let's consider some other prices. How about a price of 11? Remember, marginal cost was 10, so let's try a price of 11 and see what happens. Well, if the price is 11, what's profit? Then profit equals 11 minus 10, or 1, times 43 minus 2 times 11, or 22, so 43 minus 22, plus 20 minus 11, a little bit of mess here, but 20 minus 11 squared. So what's that equal to? That's equal to 1 times 21, plus 20 minus 11 is 9 squared. Or finally, what that equals is 81 plus 21, or 102. So 102 is bigger than 100, so we can declare some victory here. We've found a price that gives us more profit than the price that generates the profit, the price when price is equal to marginal cost. So that sounds like a good sign. We could experiment. We could try other prices. We could try P equal to 12. If we did that, what would we find? Well, then profit equals, now we'll just substitute in here, 12 minus 10 is 2. 43 minus 2 times 12, or 24, is 19. So, well, let's be careful. 43 minus 24 plus 20 minus 12, or 8 squared, and we know that's going to be 64, so let's go back here. This guy here was 19, so 2 times 19 plus 64, and so that equals 38 plus 64. And that sounds like 90 plus 8 equals 102. So that's the same profit that we had back over at a price equal to 11. So that again is bigger than 100, so we could declare some victory. We might get curious about other prices. We might think, this thing's rising when the price, if you thought about the prices, when the price is equal to 10, profit's equal to 100. The price was equal to 11, we got up to a profit of 102. The price was equal to 12, we were also at a profit of 102. Gee, I wonder if it goes even higher somewhere in between. So, we could try price equal to 11.5 just as an experiment. And if we did that, we would find that then profit equals, so again using this formula, 11.5 minus 10 is 1.5. 43 minus 2 times P, 2 times P is 23, so 43 minus 23 is 20. Plus then 20 minus 11.5 squared, so plus 8.5 squared. This would equal 1.5 times 20 is 30. 8.5 squared, well, I need a calculator to do that, but when I do that on a calculator, I find that it's 72.25. And so the sum of these is 102.25. which is actually bigger. So sure enough, 11.5 yields even bigger profit. But that's a kind of overkill. In a problem like this, I typically just say, hey, see if you can beat that price, or beat rather the profit you had when you had a price equal to marginal cost. But for the curious, we can take this one step farther and we can say, well, what's actually the profit maximizing price? So for that, again, this is not something I expect, but again, this is just for the curious. We can write profit in the following way. It's 43 times P minus 2P squared minus 430 plus 20P plus 400 minus 40P, oops, that's a 40P plus P squared. Well, that simplifies quite a lot to 23P minus P squared. Now, if we ask the question, when is this maximized? Well, the answer is going to be the derivative, d pi dp, and that's 23 minus 2p. And so indeed, if we set that equal to 0, we find that 23 over 2, which equals 11.5, is the optimal p. Okay, that's kind of overkill, but just for the curious, there it is. All right, let's talk a little bit about bundling. So here's a bundling problem where we have two consumers, kind of generically named consumer A and consumer B. We have two products, also pretty generically named, product 1 and product 2. Consumer A has a maximum willingness to pay for product 1 of 10 and a maximum willingness to pay for product 2 of 9. Consumer B has a maximum willingness to pay for product 1 of 8 and a maximum willingness to pay for product 2 of 9. First question we could say is, suppose products 1 and 2 were being sold separately. What's the best price from the standpoint of profit maximization for product 1? So best P for 1. So suppose, for example, we were to charge a price of 10. Well, then only consumer A would buy, consumer B would pass on product 1, we'd have revenue of 10. If we were to charge 9, well, only consumer A would buy, and our revenue would be 9, so that's not a very smart price. But if we went to a price of 8, then both consumers A and B would buy, and our revenue would be 2 times 8, or 16. So by that logic, the best price for 1, when sold separately, equals 8, and that gives us revenue equal to 16 for product 1. We can do the same exercise for product 2, and we'll find that the best price for 2 is 9, and that gives us revenue of 18, because then both buy, we get 2 times 9, or 18, and in the event we sell these both at their best sold separately prices, then our total revenue is going to equal 16 plus 18, or 34. Now let's just say that in this problem, just so that I haven't misspoken, let's just say that costs are 0. So revenue equals profit. And again, selling separately, the best we can do it is to get revenue and profit of 34. Well, now let's consider a new product called the bundle. The bundle has, or I should say, the consumer's maximum willingnesses to pay for the bundle are the sum of their maximum willingnesses to pay for each of the products. So if we were to define the bundle over here, we'd say that consumer A is willing to pay 10 plus 9, or 19, for the bundle. And consumer B is willing to pay 8 plus 11, or 19, for the bundle. Well, now when we ask the question, what's the best price to charge for the bundle? Best in the sense of profit maximizing? Well, the best bundle price equals 19. Then they both buy, they each pay 19. The resulting revenue is equal to 38. And what's interesting here is that 38 is bigger than 34. Now, another feature of this problem on this page right here is that when we summed up their willingnesses to pay, we entirely eliminated the variance. it turned out that they had the same willingnesses to pay for the bundle. And that meant that the price we set for the bundle was not only better from a profit generating standpoint than the selling separately prices, but it also means that we as the seller were able to get all of the willingness to pay as producer surplus. We took away all the consumer surplus. So this was a very effective instance of bundling. Okay, let's talk about the dominant firm model. And now let's have an example in which the market demand curve is our old friend, P equals 100 minus Q. And the follower supply curve is P equals 20 plus 7Q. The final feature of the model is going to be that leader marginal cost is 20. So usually the first task in these problems is to find the leader's demand curve. So let's make a picture that helps guide us through that. Q here, P here. Here let's say is 100. Here let's say is 100. That's market demand I just put down here. Then let's put in follower supply, which rises up from an intercept of 20 at a pretty steep slope. So that's follower supply. And what we know is that this intersection right here is going to be the intercept of the leader's demand curve. So what I want to do is find that intercept, and we're going to find first the quantity associated with that intercept, and then we'll find the price associated with that intercept. But let me just show you what I mean. So let's solve market demand and follower supply together. 100 minus Q equals 20 plus 7Q. So that's 100 minus 20 is 80 equals Q plus 7Q, 8Q, or of course Q equals 10. So that's 10. Now if we go up to the demand curve and ask what price is at the quantity 10 on the market demand curve, well, P equals 100 minus 10, that's 90. So we just found something. We just found that the intercept of the leader demand curve is 90. So we know that that's a point on the leader demand curve. We could just go ahead and say that the leader demand curve is P equals 90, but then we have a question mark about the intercept, something times Q. Well, we have a little bit more information here. We know that this is one point on the leader demand curve, and we know that when the price hits 20, that the market demand becomes leader demand. When the price is 20, where are we? 20 equals 100 minus 80. So that point there is 80. That means this point here is on the leader demand curve, as is this point. And we can think about slope, and we can think about it pretty clearly. This vertical distance here it's 70, but let's call it minus 70 because we're going down. This horizontal distance here is 80. That means the slope of this is 7/8. So minus 7/8 times Q. All right, so that's the leader demand curve right there. Let's proceed. Usually the next step in a problem like this is to find the leader's marginal revenue curve and set it equal to his or her marginal cost to find the leader's quantity, and so let's do that. Well, if leader demand is given by P equals what we just said, which is 90 minus 7/8 times Q, then leader's marginal revenue has the same intercept and twice the slope, so minus 7/4 times Q. If we set marginal revenue equal to marginal cost, and remember the leader's marginal cost is 20, so setting these equal to each other means 70 minus 7/4 Q equals 20. So let's subtract 20 from both sides and add 7/4 Q to both sides. Let's multiply both sides by 4 and divide both sides by 7. So we get 4 times 70 over 7 equals Q. Well, 70 over 7 is 10. 4 times 10 is 40. And so there you go. The leader produces 40 units of output. What about the price? And I don't have to call it the leader's price because although it's set by the leader, it's the price that everybody charges and everybody pays. Well, let's plug this 40 into the leader demand curve, and we'll find out what that price is. So price is equal to 90 minus 7/8 times 40. So what does that equal? Well, that's 90 minus 7 times 40 over 8. 40 over 8 is 5, so that's 90 minus 7 times 5, or 90 minus 35, and so therefore that equals 55. Okay. Now, we're not quite done, because we'd like to think about the follower's quantity of output, and we'd like to make sure that the total quantity of output equals the leader's quantity of output plus the follower's quantity. So let's find the follower quantity of output. Remember that follower supply curve here is P equals 20 plus 7 times Q. We've said that the price in the market's 55, so let's find the Q that solves that. 55 equals 20 plus 7Q. We can call that QF if we like. That means 55 minus 20, which is 35, divided by 7 equals that Q. 35 over 7 means QF equals 5. So that suggests that QL plus QF is 45, and P equals 55. Well, it turns out that's all very good news, because the market demand curve was P equals 100 minus Q. So Q here is QL plus QF, that's 45. So 100 minus 45 equals 55, and sure enough, that all kind of squares, or it doesn't kind of, that all perfectly squares together, and so we found the right answer. Good for us. All right, moving right along, let's talk about homogeneous goods duopoly. So this is that model in which two firms produce an identical product. Once again, we'll use the demand curve P equals 100 minus Q, but let's just keep in mind that Q is the sum of Q1, the output produced by firm 1, and Q2, the output produced by firm 2. Now this problem is going to be a little bit interesting in the sense that the marginal costs are not equal at the two firms. Okay, so firm 1 has marginal cost of 10, firm 2 has marginal cost of 20. So that means we have two separate tasks before us, to kind of as initial tasks in this problem. One is to find reaction curve 1, and another will be to find reaction curve 2, but we'll get there. So how do I do that? Well, let's think about firm 1's demand curve. So call that D1. It's that price equals 100 minus Q2 minus Q1. Now, that means that marginal revenue at firm 1 has the same intercept, 100 minus Q2 minus 2 times Q1. So that is the bisecting deal here, keeps the intercept the same and has twice the slope. So that's MR1. MC1 is 10, so setting MR1 equal to MC1 means solving the following equation. 100 minus Q2 minus 2Q1 equals 10. What we're solving for here is firm 1's reaction curve, so we want to solve for Q1. So what's that going to look like? Well, it's going to look like 100 minus 10 over here, so that's 90 minus Q2 over 2 equals Q1. Or Q1 equals 45 minus 1/2 times Q2. And that's firm 1's reaction curve. Okay? Now once again, because the marginal costs aren't the same at the two firms, this is not a symmetric problem. We can't just switch the subscripts to find the answer. Instead, we have to separately find firm 2's reaction curve. So let's do that. So demand at firm 2 looks like this. P equals 100 minus Q1 minus Q2. Marginal revenue at firm 2 is 100 minus Q1 minus 2 times Q2. MC at firm 2 is 20. So setting MR equal to MC at firm 2 means solving the following equation. 100 minus Q1 minus 2 times Q2 equals 20. So if I subtract 20 from each side, or from both sides, I get 80 over here minus Q1. Now let's add 2Q2 to both sides. So that equals 2Q2, but let's divide both sides by 2, save a step. And so that means that's a 2. Let's be careful. That means the reaction curve for firm 2 is equal to 40. Q2 equals 40 minus 1/2 times Q1. Okay, so that's 2's RC. And note that, as I said, this would not be a symmetric problem, and indeed it's not. In the other reaction curve, it was Q1 equals 45 minus 1/2 Q2, whereas here it's Q2 equals 40 minus 1/2 times Q1. Okay, so how do we find, we're somewhere, but we're not done. What we have to do to find the quantities of output produced by the respective firms is to solve these reaction curves together. So let's do that. And that's, by the way, finding the Carnot-Nash solution to this problem. There we go. So here's firm 1's reaction curve. Q1 equals 45 minus 1/2 Q2. If we plug firm 2's reaction curve, which by the way was Q2 equals 40 minus 1/2 Q1, so let's plug this into here, we get that Q1 equals 45 minus 1/2, that's a minus sign, times 40 minus 1/2 times Q1. So now we have an equation that just involves Q1, so if we're careful we can find the answer. And so what is the answer? Well, 45, now minus 1/2 times 40 is minus 20, minus 1/2 times 1/2, that means plus 1/4 times Q1, and that's what Q1 equals. Let's now subtract 1/4 Q1 from both sides, so we get Q1 times 3/4 equals 45 minus 20, or 25. So Q1, let's multiply both sides by 4 and divide both sides by 3. So Q1 equals 4 times 25, or 100, over 3, which is equal to 33 1/3. How about Q2? Well, if we have some faith in our arithmetic, then we can plug Q1 into firm 2's reaction curve, and we get that Q2 equals 40 minus 1/2 times Q1. Let's just call Q1 100 over 3. So that means we have 40 minus 100 over 6, or 240 over 6 minus 100 over 6, all of which equals 140 over 6, or finally 70 over 3, which we could also say is 23 1/3. Now let's step back a little bit and think about whether this makes sense. Firm 1 had lower marginal costs than firm 2. Firm 1 in the equilibrium produces more output than firm 2. That kind of makes sense. Having lower marginal costs gives you, alters your reaction curve in a way that induces you to produce more output in the equilibrium, at least in the Carnot-Nash equilibrium. Let's consider another variant on this problem, a first mover problem. But let's say that, just to keep ourselves on our toes, let's say that suppose firm 2 moves first. So in other words, we're going to do this from the perspective of firm 2, as though firm 2 is moving first. So what I want to do is characterize firm 2's demand curve. Let's start just with the general version, P equals 100 minus Q1 minus Q2. The idea here is, though, that firm 2 knows how firm 1 would react to what firm 2 does, and of course that's because firm 2 knows that firm 1's reaction curve is Q1 equals 45 minus 1/2 Q2. So if we plug this into here, we'll have what is effectively firm 2's demand curve. P equals 100 minus 45 minus 1/2 Q2 minus Q2. Now we can simplify that a bit. 100 minus 45 is 55. Minus 1/2 is, that's plus 1/2 minus 1, so it's minus 1/2 times Q2. So there's firm 2's demand curve. What is firm 2's marginal revenue curve then? Same intercept, 55, but twice the slope, so minus 1 times Q2. What's firm 2's optimal quantity of output? Well, we find that by setting MR equal to MC. What was MC at firm 2? Well, it was equal to 20. And so that means we solve 55 minus Q2 equals 20, and we get that Q2 is equal to 35. Okay? What about the price? Well, we can plug 35 units of output into that demand equation, and we get that P equals 55 minus 1/2 times 35. Okay? Or that equals, and we're getting a little tight on space here, but that equals 110 minus 35 over 2. So that's 110 minus 35 all over 2. That's also known as 75 over 2, which is also 37 and a half. Now notice that firm 2 is now producing more than it used to produce. It used to produce 27 or something, and now it's producing 37. We're running out of space here, but let's go to the next page and think about how much firm 1 produces. So remember, firm 2 is going to produce 35 units of output, and the price in the market is going to be 37.5. Okay, so we found in the last slide that firm 2 produces 35 units of output, and the price in the market for this product ends up being 75 over 2, or 37.5. But let's also ask the question, how much does firm 1 produce? Given that firm 2 moved first and chose 35 units of output, for that we just have to appeal to firm 1's reaction curve, which is 45 minus 1/2 times Q2, or in this case 1/2 times 35. And so that equals 90 minus 35 over 2, which is also known as 55 over 2, or 27.5. So notice that when firm 2 moves first, instead of producing less output, it ends up producing more output than firm 1. Okay, it produces 35, firm 1 produces 27.5. Okay, let's move on. Let's talk about an expected utility problem. So this is a problem involving the possibility of a fire. And so we have an individual whose initial wealth is 1,000, not 100, 1,000. If a fire occurs, then wealth drops by 400 to 600. The probability that a fire occurs is 2%. That means that the probability of no fire is the complement to that, or 98%, 0.98. Finally, the utility function here is square root of w, w to the 0.5, or as we sometimes note it, just the square root function of w. So the problem here is to find the maximum willingness to pay for full insurance. So the way we're going to do that is we're going to calculate the expected utility of being uninsured. So let's move and do that. So the expected utility of being uninsured is the probability of fire times the utility of wealth if fire, plus the probability of no fire times the utility of wealth if no fire. And so what's that? That's 0.02 times the utility of 600 plus 0.98 times the utility of 1,000. Again, we have particular utility functions here, so it's 0.02 times square root of 600 plus 0.98 times square root of 1,000. So we need a calculator to calculate out these numbers, but if we do that, we'll find that the answer is 31.48019. Let's look at a picture for a minute. Think about what it is we've just calculated. We've got wealth here, we've got utility here, we've got, let's say, 600 here, we've got 1,000 roughly here. Utility function has roughly this shape. the expected utility line connects this dot with this dot. I'll exaggerate things because this is kind of a fat pen. What we're saying is we're 98% of the way over from here to here. And so, in fact, the expected value of our wealth, if we're uninsured, is equal to 0.98 times 1,000 plus 0.02 times 600, which equals 992. So I'll exaggerate it in the picture and put 992 over here. But what we're looking for is a point that's 98% of the way over along this expected utility line. And that's what we've calculated, that expected utility 31.48019. And again, I've very much exaggerated the nature of the picture just to make things visible given the fat pen. Next question we can ask, though, is that what amount of wealth with certainty would leave the individual as well off as facing the uninsured state? Well, this EU level of 31.48019, that's a level of happiness associated with not being insured. The amount of wealth with certainty that leaves the individual as well off is the amount right here. So let's call this WCE. And it's an important number for us because it's going to shed some light on how much this individual is willing to pay for insurance. So let's move to the next slide and work through it. So what we're saying is there was that expected utility level that we calculated in the last slide, and that generates a level of happiness equal to the level of happiness associated with some particular level of wealth, the certainty equivalent level. So we're trying to solve for that. And let's use what we know. We know that the utility function is the square root function. We know that that expected utility amount that we calculated before was 31.48019. So that also means that if we square that, if we have 31.48019, that'll be our certainty equivalent wealth level. And sure enough, if we use a calculator, we find that that answer is about 991 and some change, 0.002 or something. Now, what does that tell us? Well, the individual starts life here with wealth equal to 1,000, but with maybe the possibility of ending up with wealth of 600. The individual would be as happy if he or she simply had 991. So let's just call it 991 to make the numbers round. That means the individual is willing to pay as much as 1,000 minus 991, or let's call it 9, for full insurance. Any price of full insurance below 9 would actually make the person better off. Let's compare what they're willing to pay for this full insurance to the expected cost of offering this full insurance. What does this full insurance pay out? Well, 2% of the time it pays 400. The other time it pays 0. So what's 2% of 400? Well, that's 8. So it costs 8 to offer. It's worth 9 to this potentially insured person. And so that shows how, first of all, what the person's willing to pay for the insurance, and secondly, the interesting lesson that they're willing to pay more for it than it costs to offer it, and so it can make both of them better off. All right, let's move on. Let's talk a bit about public goods allocation. So let's think about a problem where there are three consumers. There are three consumers in the economy, and they have these various different marginal valuation functions for the public good in question. So consumer A has MVA equal to 10 minus Q. Consumer B has MVB equal to 20 minus 2Q. And consumer C has valuation 5 minus a half Q. What we need to do is to figure out the vertical summation of these marginal valuation functions to get to the MVT, the total. And what that is here is 10 plus 20 plus 5 minus 1 plus 2 plus a half times Q, or it equals 35 minus 3.5 times Q. Let's say that the marginal cost of this item, and let's be clear what that is the marginal cost of, It's the marginal cost of the unit of the public good. So let's say if it's lighthouses or something, it's the cost of an additional lighthouse. It's not the cost of an additional consumer using a lighthouse. That is zero. But the cost of adding another one of these things, the lighthouse or the radio broadcast station or the laser missile system or whatever you like, that's what's going to be equal to this number, 3.5. So what we're looking for to find the answer here is the place where the MVT function crosses MC. And that's the quantity in question. So how do we do that? Well, we set this equal to this and find Q. So 35 minus 3.5 Q equals 3.5. And if we solve that, we get that Q equals 9. And there you have it. That's the optimal quantity of this public good. Now, I think the tricky part of this question, if there is a tricky part, is just to remember that vertical summation requires us to express the marginal valuation functions for each consumer the way we have here, and then we can add them up to get to the marginal value across all of consumers. All right, let's talk about a bit about externalities. So what is an externality? It's a situation in which, say, the consumption of a product confers a benefit on a third party. So that would be an example of a positive externality in consumption. So let's think about the example of vaccination. So if I go out and get vaccinated, I certainly confer a benefit on myself because I reduce the probability that I'm going to contract some horrible illness. But I also reduce the probability that you will contract this horrible illness because if I can't get it, then I can't give it to you. And so that means that there's a divergence between what it is that causes my own demand, which is my own benefit, and the overall social benefit of doing it. And so that means that the thing that we have traditionally called demand, we might alternatively label the marginal private benefit, MPB. So there's marginal private benefit. There's the supply function. It's not clear if it's going to be an increasing cost good or not. But then what's important in this problem here is that there's this social benefit that exceeds the private benefit because there's an additional benefit to other people from my getting vaccinated. So let's add a new curve here, the marginal social benefit of vaccination. Now once we do this, and by the way I should label my axes P and Q, this guy here, marginal private benefit, is just what we used to call demand. The intersection of supply and demand does still determine what actually happens. So that's the actual quantity of vaccinations that get purchased and obtained and consumed in society, but it's not the optimal quantity. The optimal quantity is right here. We'll call it Q star. And moreover, the situation, the market left to itself, produces deadweight loss. Where's the deadweight loss? Well, let's think about where the market stops at Q actual. If one more unit had been consumed, this is the marginal benefit that would have been experienced, and this is the cost. So there would have been this surplus, but it doesn't happen. And ditto for this unit, and so forth. So this whole region is deadweight loss, and it's deadweight loss of the sort that is missed opportunities for surplus. So we stopped before we should have. That's what that means. Okay, so there's a review of the major kinds of problems that we've covered since the midterm. Again, we can't do the whole course in an hour or whatever this has been, but this is certainly a good introduction or a good refresher about how to study for the final or the last exam. And I wish you well, and think it'll all work out okay.